Hey everyone, welcome back. In the previous video, we talked about hypothesis testing, specifically z-test. So here are the assumptions behind the z-test. So the samples are independent and random, and the sample size is large enough and or population variance is known. So if the population variance is known, so we can calculate the z-score using this formula where x bar is the sample mean and mu is the population mean under the null hypothesis, and sigma is the population standard deviation, and n is the sample size. And the z follows a standard normal distribution. If population variance is unknown, but our sample size is large enough because of the central limit theorem, so we know that the sample mean follows a normal distribution. We still can use the sample variance to approach the population variance. And we can still calculate the z-score using this formula. However, in many practical scenarios, we face situations where the sample size is less than 30 and or the population variance is unknown. So in such cases, the z-test is no longer suitable. Okay, so we turn to the t-distribution. T-distribution is also called the student's t-distribution, and when we calculate the test statistic, we use the sample standard deviation instead of the population standard deviation. And the test statistic follows a t-distribution with a degree of freedom equals n-1. Okay, so here's how you calculate the sample standard deviation. You may wonder why n-1 degrees of freedom. When we take n samples from the population, there's no restriction. So the degrees of freedom is n. However, after calculating the sample mean, the x bar, we now have a constraint as follows. The sum of all the x values should be equal to n times the sample mean. Okay, so for example, if you take the first n-1 samples and the last sample should be fixed because of this constraint. And also degrees of freedom refers to the number of independent observations in a sample of data. Let's dive into the t-distribution. The t-distribution is a type of probability distribution that is symmetric and bell-shaped like a normal distribution, but with heavier tails. So it generalizes the standard normal distribution. Okay, as you can see here, this is a t-distribution with 10 degrees of freedom. Let's compare the t-distribution with the standard normal distribution. So here is a plot of t-distributions with different degrees of freedom and a standard normal distribution. So the orange curve is the t-distribution with 1 degree of freedom, and the purple represents a 2 degrees of freedom. And the blue one represents the 5 degrees of freedom, and the black curve is the distribution with an infinite number of degrees of freedom. And the red dashed bell curve represents the standard normal distribution. Okay, as you can see that t-distributions with a lower degrees of freedom have lower peak and heavier tail. As the sample size increases, leading to a greater number of degrees of freedom, the t-distribution gradually converges to a z-distribution. This is because larger samples give us a better estimate of the population standard deviation. And there's one thing I want to mention here is that the SD function in R uses the denominator n-1. So let's recall the steps for a hypothesis testing. So the first step is state the null and alternative hypothesis, and then you specify the significance level, alpha, and then you compute the test statistic. In the t-test is t. You can use the critical value method, or you can compute the p-value and then use the p-value method to make your decision. And the final step is state your conclusion. So there are 3 types of t-tests. The first one is one sample t-test. It is used to verify a claim about the population mean. And the second one is 2 sample t-test to compare 2 population means. And the last one is paired t-test. So you compare 2 population means with paired data. The paired data means that The data comes from the same subjects but at the different times or under two different conditions. So let's look at some examples about the one sample t-test. The first one is a computer software company claims that a new version of its operating system will crash fewer than 6 times per year on average. A system administrator installs operating system on a random sample of 41 computers. At the end of the year, the sample mean number of crashes is 7.1 with the standard deviation of 3.6. So can you conclude that the vendor's claim is false? Use the alpha equal to 0.05 significance level. Okay, so let's check the assumptions. So the samples are random, right? We have random sample and we have 41 samples. And then this is our sample mean and sample standard deviation. Our population variance is unknown, so we apply our t-test. So let's state our null and alternative hypothesis. So the null hypothesis is the mu is equal to 6, and the alternative hypothesis is mu is greater than 6. If we want to conclude that the vendor's claim is false, so the number of crashes should be greater than 6. Right, so we have the x bar is equal to 7.1 standard deviation, sample standard deviation is equal to 3.6, and mu is equal to 6, and the sample size is 41. Okay, so we plug into x bar minus mu divided by sample standard deviation divided by square root of n, and we calculate the t critical values, and also we calculate the p-value. Okay, so notice here, so we set lower dot-tail equal to false because the default for the lower dot-tail in the PT function is true. And then we also calculate the confidence interval. So we got the t statistic is 1.957 and the t critical value is 1.684 and our p-value is 0.029 and the confidence interval is from 6.153 to 8.047. Because our t statistic is greater than the critical value and p-value is less than 0.05, so we reject the null hypothesis and conclude that the vendor's claim is false. Let's look at another example of one sample t-test. So this time we have our raw data. So suppose you have a batch of batteries and the manufacturer claims that these batteries last an average of 300 hours. So you want to test this claim by taking a sample of batteries and testing their lifespan. So here's the other lifespans of the batteries. And then the first step is you state the null and alternative hypothesis. So null hypothesis is mu is equal to 300 and our alternative hypothesis is mu is not equal to 300. So it's a two-tailed test. And then we prepare our raw data. We set it as batteries here. And then we calculate the mean is 300 and 301.8. The sample standard deviation is 11.887. Okay, so instead of plugging all the numbers and calculate the t statistic, we will use t.test and plug in the raw data. Okay, so here we set the mu is equal to 300 and alternative is equal to 2-sided and confidence interval equal to 0.95. So t-test will give us everything we need, such as t statistic, test the statistic, degrees of freedom, p-value, and confidence interval. And because the p-value is greater than 0.05, so we fail to reject HO at alpha is equal to 0.05 and conclude that there is no enough evidence to conclude that the mean lifespan of the battery is different from 300 hours. And also you can see that the 95% of confidence interval actually contains 300. And then we're going to take a look at two sample t-test. But before we do that, I need to introduce another concept, pooled variance. Okay, so when the population variances are equal or are assumed to be equal, so we can pool the sample variances. So what is a pooled sample variance? The pooled variance is a weighted average of the sample variances. Here is how you calculate the pooled variance. So you can use Levene test from car package to test the equality of variances. But this is beyond the scope of this video. And a common rule of thumb is that if the largest sample standard deviation is not more than twice the smallest standard deviation, then the variances are considered equal. And we can set var.equal equals to true in t.test function. So here is how you calculate the test statistic using the pooled variance. Let's take a look at one example of two sample t-test. So suppose you want to compare the average lifespan of two different brands of batteries. So here is the raw data from brand A, and here is the raw data from brand B. Now we state our null and alternative hypothesis. So the null hypothesis states that the mu A is equal to mu B, or we can state mu A is minus mu B is equal to 0, okay? And the alternative hypothesis is mu A is not equal to mu B. And then we prepare our raw data, okay? We calculate the sample mean, and we calculate the sample standard deviation. And then we use t.test. We plug in these two vectors here, and we set the alternative is equal to 2.cited, and also we set the var.equal equals to true. So here is the result from the t-test. Our t-statistic is equal to 2.2361, and degrees of freedom is equal to 20, and the p-value is 0.03969, and the 95% confidence interval is 0.64 to 18.46. And then because the p-value is less than 0.05, so we reject the null hypothesis at alpha equal to 0.05, and I conclude that the mean lifespan of the batteries is different between the two brands. And then the last one is pair t-test. So you are testing the effectiveness of a new diet program. A group of individuals' weights are recorded before starting the program and after completing the program. So here are the weights before the program, and here are the weights after the program. We state our null hypothesis as mu before minus mu after is equal to 0. So for the alternative hypothesis is mu before minus mu after is greater than 0. This is going to be a right tail test, or you can state mu after minus mu before is less than 0. And this is going to be a left tail test, okay? So both are correct, but this will affect how we plug in our raw data to t.test function, as we will see later. Okay, we prepare our raw data, so before and after. So we calculate the sample mean and the sample means of before and sample means of after. So if it is a right tail test, so we will set the before first and after second, and we set alternative is equal to greater, because our alternative hypothesis is the mean of the before is greater than the mean of the after, right? And we set the paired equal to true. So if we pick the second option, like a left tail test, then we will put our after before the before, okay? And we'll set the alternative equal to less, okay? So both are true, but you have to be careful for the order of the data and the value for alternative. Our test statistic is 2.8892, and degrees of freedom is equal to 9, and p-value is equal to 0.008954, and our 95% confidence interval is 5.40 to infinity. Okay, so because the p-value is less than 0.05, we're going to reject the null hypothesis at alpha equal to 0.05, and I conclude that the mean weight before and after the diet program is different. So right now we have we compare the means at most two groups, right? So what if we have more than two groups? And how do we detect if there is a difference between the groups? This is where ANOVA comes into play, which is our topic of the next video. Stay tuned. If you find this video helpful, please like and subscribe. Thank you for watching.